Introduction to Activity Planning. In this video, we are going to see about Introduction to Activity Planning. A detailed plan for the project includes a schedule indicating the start and completion times for each activity. This will enable us to ensure that the appropriate resources will be available precisely when required. Avoid different activities competing for the same resources at the same time. Produce a detailed schedule showing which staff carry out each activity. Produce a detailed plan against which actual achievement may be measured. Produce a timed cash flow forecast. Replan the project during its life to correct drift from the target. To be effective, a plan must be stated as a set of targets, the achievement or non-achievement of which can be unambiguously measured. The activity plan does this by providing a target start and completion date for each activity or a window within which each activity may be carried out. The starts and completions of activities must be clearly visible, and this is one of the reasons why it is advisable to ensure that each and every project activity produces some tangible product or deliverable. Monitoring the project's progress is then, at least in part, a case of ensuring that the products of each activity are delivered on time. Much of the job of project management concerns recognizing when something has gone wrong, identifying its causes, and revising the plan to mitigate its effects. The objectives of activity planning. In addition to provide project and resource schedules, activity planning aims to achieve a number of other objectives which may be summarized as follows. Feasibility assessment. Is the project possible within required timescales and resource constraints? It is not until we have constructed a detailed plan that we can forecast a completion date with any reasonable knowledge of its achievability. Resources allocation. What are the most effective ways of allocating resources to the project? When should resources be available? The project plan allows us to investigate the relationship between timescales and resources availability. That is, in general, allocating additional resources to a project shortens its duration and the efficiency of additional spending on resource procurement. Detailed costing. How much will the project cost and when is that expenditure likely to take place? After producing an activity plan and allocating specific resources, we can obtain more detailed estimates of costs and their timing. Motivation. Providing targets and being seen to monitor achievement against targets is an effective way of motivating staff, particularly where they have been involved in setting those targets in the first place. Coordination. When do the staff in different departments need to be available to work on a particular project, and when do staff need to be transferred between projects? The project plan, particular with large projects involving more than a single project team, provides an effective vehicle for communication and coordination among teams. In situations where staff may need to be transferred between project teams or work concurrently on more than one project, a set of integrated project schedules should ensure that such staffs are available when required and do not suffer periods of enforced idleness. Activity planning and scheduling technique places an emphasis on completing the project in a minimum time at an acceptable cost, or alternatively meeting a set target date at minimum cost. One effective way of shortening project durations is to carry out activities in parallel. When to plan. In this video, we are going to see about when to plan. Planning is an ongoing process of refinement, each iteration becoming more detailed and more accurate than the last. Over successive iteration, the emphasis and purpose of planning will shift. During the feasibility study and project startup, the main purpose of planning will be to estimate timescales and the risks of not achieving target completion dates or keeping within budget. As the project proceeds beyond the feasibility study, the emphasis will be placed upon the production of activity plans for ensuring resource availability and cash flow control. Throughout the project, until the final deliverable has reached the customer, monitoring and replanning must continue to correct any drift that might prevent meeting time or cost targets. Before work commences on a project or possibly a stage of a larger project, the project plan must be developed to the level of showing dates, when each activity should start and finish, and when and how much of each resource will be required. Once the plan has been refined to this level of detail, we call it a project schedule. Creating a project schedule comprises of 4 main stages. The first step in producing the plan is to decide what activities need to be carried out and in what order they are to be done. From this, we can construct an ideal activity plan, that is, a plan of when each activity would ideally be undertaken, where resources not a constraint. This activity plan is generated by steps 4 and 5 of stepwise. The ideal activity plan will then be the subject of an activity risk analysis aimed at identifying potential problems. This might suggest alterations to the ideal activity plan and will almost certainly have implications for resource allocation. The expected availability of resources might place constraints on when certain activities can be carried out, and our ideal plan might need to be adapted to take account of this. The final step is schedule production. Once resources have been allocated to each activity, we will be in a position to draw up and publish a project schedule which indicates planned start and completion dates and a resource requirement statement for each activity. Projects and activities. In this video, we are going to see about projects and activities. A project is composed of a number of interrelated activities. A project may start when at least one of its activities is ready to start. A project will be completed when all of the activities it encompasses have been completed. An activity must have a clearly defined start and a clearly defined end point, normally marked by the production of a tangible deliverable. If an activity requires a resource, as most do, then that resource requirement must be forecastable and is assumed to be required at a constant level throughout the duration of the activity. The duration of an activity must be forecastable, assuming normal circumstances and a reasonable availability of resources. Some activities might require that others are completed before they can begin. These are known as precedence requirements. Identifying activities. Essentially, there are three approaches to identify the activities or tasks that make up a project. We shall call them the activity-based approach, the product-based approach, and the hybrid approach. The activity-based approach. The activity-based approach consists of creating a list of all the activities that the project is thought to involve. This might require a brainstorming session involving the whole project team, or it might stem from an analysis of similar past projects. When listing activities, particularly for a large project, it might be helpful to subdivide the project into the main life cycle stages and consider each of these separately. Rather than doing this in an ad hoc manner, with the obvious risks of omitting or double counting tasks, a much favored way of generating a task list is to create a work breakdown structure, that is WBS. This involves identifying the main or high-level tasks required to complete a project and then breaking each of these down into a set of lower-level tasks. A fragment of a WBS where the design task has been broken down into 3 tasks and one of these has been further decomposed into 2 tasks. Activities are added to a branch in the structure if they contribute directly to the task immediately above. If they do not contribute to the parent task, then they should not be added to that branch. When preparing a WBS, consideration must be given to the final level of detail or depth of the structure. Too great a depth will result in a large number of small tasks that will be difficult to manage, whereas a too shallow structure will provide insufficient detail for project control. Each branch should, however, be broken down at least to a level where each leaf must be assigned to an individual or responsible section within the organization. Advantages claimed for the WBS approach include the belief that it is much more likely to result in a task catalog that is complete and is composed of non-overlapping activities. The product-based approach. The product-based approach used in Prince 2 and stepwise. The PFD indicates for each product which other products are required as inputs. The PFD can therefore be easily transformed into an ordered list of activities by identifying the transformations that turn some products into others. This approach is particularly appropriate if using a methodology such as SSADM or USDP, that is Unified Software Development Process, which clearly specifies for each step or task each of the products required and the activities required to produce it. For example, the SSADM reference manual provides a set of generic PBS for each stage in SSADM, which can be used as a basis for generating a project-specific PBS. In the USDP, products are referred to as the artifacts, and the sequence activities needed to create them is called a workflow. For an example, USDP emphasizes that processes are iterative. This means that it may not be possible to map a USDP process directly onto a single activity in a network. All projects, whether they contain iterations or not, will need to have fixed milestones or time boxes if progress towards a planned delivery date is to be maintained. These larger activities with the fixed completion dates would be the basis of the activity network. The hybrid approach, WBS illustrated, is based entirely on structuring of activities. More commonly, a WBS may be based upon the project's products as illustrated, which in turn based on a simple list of final deliverables, and for each deliverable, a set of activities required to produce that product. Beneficial to introduce additional levels structuring both products and activities. The degree to which the structuring is product-based or activity-based might be influenced by the nature of the project and the particular development method adopted. As with a purely activity-based WBS, having identified the activities, we are then left with the task of sequencing them. A framework dictating the number of levels and the nature of each level in the structure may be imposed on a WBS. For example, in their MITP methodology, IBM recommend that the following 5 levels should be used in a WBS. Level 1 Project. Level 2 Deliverables such as software manuals and training courses. Level 3 Components, which are the key work items needed to produce deliverables, such as the modules and tests required to produce the system software. Level 4 Work packages, which are major work items or collections of related tasks required to produce a component. Level 5 Tasks, which are tasks that will normally be the responsibility of a single person. Sequencing and scheduling activities. In this video, we are going to see about sequencing and scheduling activities. Throughout a project, we will require a schedule that clearly indicates the project's activities is planned to occur and what resources it will need. Let us consider in outline how we might present a schedule for a small project. One way of presenting such a plan is to use a bar chart. In drawing up the chart, we have therefore done two things. We have sequenced the task, that is, the scheduling has had to take account of the availability of staff and the ways in which the activities have been allocated to them. In the case of small projects, this combined sequencing scheduling approach might be quite suitable, particularly where we wish to allocate individuals to particular tasks at an early planning stage. However, on larger projects, it is better to separate out these two activities to sequence the tasks according to their logical relationships and then to schedule them taking into account resources and other factors. Network planning models. These project scheduling techniques model the project's activities and their relationships as a network. In the network, time flows from left to right. These techniques were originally developed in the 1950s, the two best known being CPM, that is Critical Path Method, and PERT, that is Program Evaluation Review Technique. Both of these techniques used an activity-on-arrow approach to visualize the project as a network where activities are drawn as arrows joining circles or nodes which represent the possible start and or completion of an activity or set of activities. More recently, a variation on these techniques called precedence networks has become popular. This method uses activity-on-node networks where activities are represented as nodes and the links between nodes represent precedence or sequencing requirements. This latter approach avoids some of the problems inherent in the activity-on-arrow representation and provides more scope for easily representing certain situations. It is this method that is adopted in the majority of computer applications currently available. These three methods are very similar, and it must be admitted that many people use the same name, particularly CPM, indiscriminately to refer to any or all of the methods. Formulating a network model. In this video, we are going to see about formulating a network model. The first stage in creating a network model is to represent the activities and their interrelationships as a graph. In activity-on-node, we do this by representing activities as nodes, that is boxes in the graph. The lines between nodes represents dependencies. Constructing precedence networks. A project network should have only one start node, although it is logically possible to draw a network with more than one starting node. It is desirable to do so as it is a potential source of confusion. In such cases, for example, where more than one activity can start which has zero duration but may have an actual start date. A project network should have only one end node. The end node designates the completion of the project, and a project may finish only once. Although it is possible to draw a network with more than one end node, it will almost certainly lead to confusion if this is done. A node has duration. A node represents an activity, and in general, activities take time to execute. However, that the network does not contain any reference to durations. This network drawing merely represents the logic of the project, the rules governing the order in which activities ought to be carried out. Links normally have no duration links. Links. It represents the relationships between activities. The installation cannot start until program testing is complete. Program testing cannot start until both coding and data take-on have been completed. Precedents are the immediate preceding activities. In figure, the activity program test cannot start until both code and data take-on have been completed, and activity install cannot start until program test has finished. Code and data take-on can therefore be said to be precedents of program test, and program test is a precedent of install. The code and data take on as precedence of install. That relationship is implicit in the previous statement. Time moves from left to right. If at all possible, networks are drawn so that time moves from left to right. It is rare that this convention needs to be flouted, but some people add arrows to the lines to give a stronger visual indication of the time flow of a project. A network may not contain loops. A loop is an error in that it represents a situation that cannot occur in practice. While loops in the sense of iteration may occur in practice, they cannot be directly represented in a project network. The logic of figure suggests that program testing cannot start until the errors have been corrected. If the number of times is expected to repeat a set of activities, a test diagnose correct sequence, for example, then one can draw that set of activities as a straight sequence, repeating it the appropriate number of times. If many times a sequence is going to be repeated, then it cannot calculate the duration of the project unless it adopts an alternative strategy, such as redefining the complete sequence as a single activity and estimating how long it will take to complete it. All network planning applications will detect loops and generate error messages when they are found. A network should not contain tangles. A dangling activity such as write user manual should not exist, as it is likely to lead to errors in subsequent analysis. Indeed, in many cases, dangling activities indicate errors in logic when activities are added as an afterthought. The project is complete once the software has been installed and the user manual written, then it should redraw the network with the final completion activity, which at least in this case is probably a more accurate representation of what should happen. Representing lagged activities. It might come across situations to undertake two activities in parallel so long as there is a lag between the two. It might wish to document amendments to a program as it is being tested, particularly if evaluating a prototype. In such a case, we could designate an activity, test and document amendments. This would, however, make it impossible to show that amendment recording could start one day after testing had begun and finish a little after the completion of testing. Where activities can occur in parallel with a time lag between them, which represent the lag with the duration on the linking arrow as shown. This indicates that documenting amendments can start one day after the start of prototype testing and will be completed 2 days after prototype testing is completed. Hammock Activities. Hammock activities are activities which in themselves have zero duration but are assumed to start at the same time as the first hammock activity and to end at the same time as the last one. They are normally used for representing overhead costs or other resources that will be incurred or used at the constant rate over the duration of the set of activities. Labeling conventions. There are a number of differing conventions that have been adopted for entering information on an activity or node network. The activity label is usually a code developed to uniquely identify the activity and may incorporate a project code. The activity description will normally be a brief activity name such as test take-on module. Adding the time division. The critical path approach is concerned with two primary objectives: planning the project in such a way that it gets completed as quick as possible, and identifying those activities where a delay in their execution is likely to affect the overall end date of the project or later activities' start dates. The method requires that for each activity have an estimate of its duration. The network is then analyzed by carrying out a forward pass to calculate the earliest dates at which activities may commence and the project be completed, and a backward pass to calculate the latest start dates for activities and the critical path. Forward pass and backward pass. In this video, we are going to see about forward pass and backward pass. The forward pass is carried out to calculate the earliest dates on which each activity may be started and completed. Where an actual start date is known, the calculations may be carried out using actual dates. The forward pass and the calculation of earliest start dates are carried out according to the following reasons. Activities A, B, and F may start immediately, so the earliest date for their start is 0. Activity A will take 6 weeks, so the earliest it can finish is week 6. Activity B will take 4 weeks, so the earliest it can finish is week 4. Activity F will take 10 weeks, so the earliest it can finish is week 10. Activity C can start as soon as A has finished, so its earliest start date is week 6. It will take 3 weeks, so the earliest it can finish is week 9. Activity D and E can start as soon as B is completed, so the earliest they can each start is week 4. Activity D, which will take 4 weeks, can therefore finish by week 8, and Activity E, which will take 3 weeks, can therefore finish by week 7. Activity G cannot start until both E and F have been completed. It cannot therefore start until week 10, the later of week 7 for Activity E and 10 for Activity F. It takes 3 weeks and finishes in week 13. Similarly, Activity H cannot start until week 9, the later of the two earliest finish dates for the preceding activities C and D. The project will be completed when both activities H and G have been completed. Thus, the earliest project completion date will be the later of weeks 11 and 13, that is week 13. The backward pass. The second stage in the analysis of a critical path network is to carry out a backward pass to calculate the latest date at which each activity may be started and finished without delaying the end date of the project. In calculating the latest dates, assume that the latest finish date for the project is the same as the earliest finish date, that is, to complete the project as early as possible. The latest activity dates are calculated as follows. The latest completion date for activities G and H is assumed to be week 13. Activity H must therefore start at week 11 at the latest, that is 13 minus 2, and the latest start date for activity G is week 10, that is 13 minus 3. The latest completion date for activities C and D is the latest date at which activity H must start, that is week 11. They therefore have latest start dates of the week 8, that is 11 minus 3, and week 7, 11 minus 4 respectively. Activities E and F must be completed by week 10, so their earliest start dates are week 7, that is 10 minus 3, and 0, that is 10 minus 10 respectively. Activity B must be completed by week 7. The latest start date for both activities D and E, so its latest start is week 3, that is 7 minus 4. Activity A must be completed by week 8, that is the latest start date for activity C, so its latest start is week 2, that is 8 minus 6. The latest start date for the project start is the earliest of the latest start dates for activities A, B, and F. This is week 0. Identifying the critical path. In this video, we are going to see about identifying the critical path. There will be at least one path through the network, that is, one set of successive activities that defines the duration of the project. This is known as the critical path. Any delay to any activity on this critical path will delay the completion of the project. The difference between an activity's earliest start date and its latest start date, or equally the difference between its earliest and latest finish dates, is known as the activity's float. It is a measure of how much the start or completion of an activity may be delayed without affecting the end date of the project. Any activity with a float of 0 is critical in the sense that any delay in carrying out the activity will delay the completion date of the project as a whole. There will always be at least one path through the network joining those critical activities. This path is known as the critical path and shown. The significance of the critical path is twofold. In managing the project, we must pay particular attention to monitor activities on the critical path so that the effects of any delay or resource unavailability are detected and corrected at the earliest opportunity. In planning the project, it is a critical path to be shortened to reduce the overall duration of the project. This is the difference between the earliest start date and the latest finish date and is a measure of the maximum time allowable for the activity. Activity float. Although the total float is shown for each activity, it really belongs to a path through the network. Activities A and C each have 2 weeks total float. If, however, activity A uses up its float, that is, it is not completed until week 8, then activity B will have 0 float. It will become critical. In such circumstances, it may be misleading and detrimental to the project's success to publicize total float. There are a number of other measures of activity float, including the following. Interfering float. the time by which an activity may be delayed without affecting any subsequent activity. It is calculated as the difference between the earliest completion date for the activity and the earliest start date of the succeeding activity. Interfering float. The difference between the total float and free float. This is quite commonly used, particularly in association with the free float. Once the free float has been used, or if it is zero, the interfering float tells us by how much the activity may be delayed without delaying the project end date, even though it will delay the start of subsequent activities. Shortening the project duration. In this video, we are going to see about shortening the project duration. If we wish to shorten the overall duration of a project, we would normally consider attempting to reduce activity durations. In many cases, this can be done by applying more resources to the task, working overtime, or procuring additional staff, for example. The critical path indicates where we must look to save time. If we are trying to bring forward the end date of the project, there is clearly no point in attempting to shorten non-critical activities. It can be seen that we could complete the project in week 12 by reducing the duration of activity F by 1 week to 9 weeks. As we reduce activity times along the critical path, we must continually check for any new critical path emerging and redirect our attention where necessary. Further savings, if needed, must be sought in a consideration of our work methods and by questioning the logical sequencing of activities. Generally, time savings are to be found by increasing the amount of parallelism in the network and the removal of bottlenecks, that is subject always, of course, to resource and quality constraints. Identifying critical activities. The critical path identifies those activities which are critical to the end date of the project. However, activities that are not on the critical path may become critical. As the project proceeds, activities will invariably use up some of their float, and this will require a periodic recalculation of the network. As soon as the activities along a particular path use up their total float, then that path will become a critical path and a number of hitherto non-critical activities will suddenly become critical. Therefore, common practice to identify near critical paths, those whose lengths are within, say, 10 to 20% of the duration of the critical path, or those with a total float of less than, say, 10% of the project's and completed duration. Identifying these activities is an important step in risk analysis, resource allocation, and project monitoring. Activity on arrow networks. In this video, we are going to see about activity on arrow networks. The developers of the SPM and PERT methods both originally used activity on arrow networks. In activity on arrow networks, activities are represented by links, or arrows, and the nodes represent events of activities or group of activities starting or finishing. Activity on arrow network rules and conventions. A project network may have only one start node. This is a requirement of activity on arrow networks rather than merely desirable as in the case with activity on node networks. A project network may have only one end node. A link has duration. a link represents an activity, and in general, activities take time to execute. Nodes have no duration. Nodes are events and as such are instantaneous points in time. The source node is the event of the project becoming ready to start, and the sync node is the event of the project becoming completed. Node 3 is the event that both coding and data take on, have been completed, and the activity program test is free to start. Installation may be started only when event 4 has been achieved, that is, as soon as program test has been completed. Time moves from left to right as nodes are numbered sequentially. There are no precise rules about node numbering, but nodes should be numbered so that head nodes, that is, those at the arrow end of an activity, always have a higher number than tail events, those at the non-arrow end of an activity. This convention makes it easy to spot loops. A network may not contain loops. Loops are either an error of logic or a situation that must be resolved by itemizing iteration of activity group. A network may not contain dangles. A dangling activity such as write user manual cannot exist, as it would suggest there are two completion points for the project. Node 5 represents the true project completion point, and there are no activities dependent on activity write user manual. Then the network should be redrawn so that activity write user manual starts at node 2 and terminates at node 5. In practice, we would need to insert a dummy activity between nodes 3 and 5. In other words, all events except the first and the last must have at least one activity entering them and at least one activity leaving them, and all activities must start and end with an event. Using dummy activities. When two paths within a network have a common event although they are in other aspects independent, a logical error such as that illustrates it is necessary to specify a certain piece of hardware before placing an order for it and before coding the software. Before coding the software, it is also necessary to specify the appropriate data structures, although clearly we do not need to wait for this to be done before the hardware is ordered. It requires both hardware specification and data structure design to be completed before either an order may be placed or software coding may commence. We can resolve this problem by separating the two more or less independent parts and introducing a dummy activity to the link completion of specify hardware to the start of the activity code software. This effectively breaks the link between data structure design and placing the order and is shown. Dummy activities shown as dotted lines on the network diagram. We have a zero duration and use no resources. They are often used to aid in the layout of network drawings as in the use of a dummy activity where two activities share the same start and end nodes makes it easier to distinguish the activity endpoints. These are problems that do not occur with activity or node networks. network analysis. Analysis proceeds in the same way as with activity on node networks, although the discussion places emphasis on the events rather than activity start and completion times. The forward pass. The forward pass is carried out to calculate the earliest date on which each event may be achieved and the earliest dates on which each activity may be started and completed. The earliest date for an event is the earliest date by which all activities upon which depends can be completed. Using figure and table 1, the earliest date for an event is the earliest date by which all activities upon which depends can be completed. Using figure, activities A, B, and F may start immediately, so the earliest date for event 1 is 0 and the earliest start date for these 3 activities is also 0. Activity A will take 6 weeks, so the earliest it can finish is week 6 recorded in the activity table. Therefore, the earliest we can achieve event 2 is week 6. Activity B will take 4 weeks, so the earliest it can finish and the earliest we can achieve event 3 is week 4. Activity F will take 10 weeks, so the earliest it can finish is week 10. We cannot, however, tell whether or not this is also the earliest date that we can achieve event 5 since we have not as yet calculated when activity E will finish. Activity E can start as early as week 4, the earliest date for event 3, and since it is forecasted to take 3 weeks, will be completed at the earliest at the end of week 7. Event 5 may be achieved when both E and F have been completed, that is, week 10, the later of 7 and 10. Similarly, we can reason that event 4 will have an earliest date of week 9. This is the later of the earliest finish for activity D, that is week 8, and the earliest finish for activity C, that is week 9. The earliest date for the completion of the project, event 6, is therefore the end of week 13, the later of 11, the earliest finish for H, and 13, the earliest finish for G. The results of the forward pass are shown in figure and table 3. The backward pass. The second stage is to carry out a backward pass to calculate the latest date at which each event may be achieved and each activity started and finished without delaying the end date of the project. The latest date for an event is the latest date by which all immediate following activities must be started for the project to be completed on time. As with activity on node networks, we assume that the latest finish date for the project is the same as the earliest finish date, that is, we wish to complete the project as early as possible. Identifying the critical path. The critical path is identified in a way similar to that used in activity on node networks. However, use a different concept, that of slack, in identifying the path. Slack is the difference between the earliest date and the latest date for an event. It is a measure of how late an event may be without affecting the end date of the project. The critical path is the path joining all nodes with a zero slack. Work breakdown structure. In this video, we are going to see about work breakdown structure. The foundation of the traditional approach to project management is a work breakdown structure, that is WBS. The WBS is a hierarchical description of the work that must be done to complete the project as defined in the project overview statement, that is POS. With the WBS in place, the project team can go about the task of creating comprehensive project plan including the schedule, resource requirements, and budget. In many other project situations, it is not possible to build a WBS, at least not at the beginning of the project. There are several approaches to build the WBS. The WBS is only as good as the project manager deems it to be. After all, the project manager has to manage the project and so should be the single individual that says the WBS is appropriate. The first term is activity. An activity is simply a chunk of work. The second term is task. Note that activities turn to tasks at some level in the hierarchy. A task is a smaller chunk of work. The terms activity and task have been used interchangeably among project managers and project management software packages. Higher level work as activities which are made up of tasks. The term work package. The term is familiar to most professionals. A work package is a complete description of how the tasks that make up an activity will actually be done. It includes a description of the what, who, when, and how of the work. Breaking down work into a hierarchy of activities, tasks, and work packages is called decomposition. The goal statement from the POS is defined as a level 0 activity in the WBS. The next level, level 1, is a decomposition of the level 0 activity into a set of activities defined as level 1 activities. These level 1 activities are major chunks of work. When the work associated with each level 1 activity is complete, the level 0 activity is incomplete. For this example, that means that the project is complete. As a general rule, when an activity at level n is decomposed into a set of activities at level n+1 and the work associated with those activities is complete, the activity at level n from which they were defined is complete. Decomposition is important to the overall project plan because it allows to estimate the duration of the project, determine the required resources, and schedule the work. The activities at the lowest levels of decomposition will possess known properties that allow to meet planning and scheduling needs. The lowest level activities that meet the 6 criteria are called tasks. Generating the WBS. In this video, we are going to see about generating the WBS. There are 2 fundamental approaches that can be used to identify project activities and tasks. The first is the top-down approach, the second is the bottom-up approach. Top-down approach. The top-down approach begins at the goal level and successively partitions work down to lower levels of definition until the participants are satisfied that the work has been sufficiently defined and they have reached the task level as determined by the completion criteria. 2 variations of the top-down approach, the team approach and the sub-team approach. Team approach. The team approach, while it requires more time to complete than the sub-team approach, is the better of the two. In this approach, the entire team works on all parts of the WBS. For each level 1 activity, appoint the most knowledgeable member of the planning team to facilitate the further decomposition of that part of the WBS. Continue with similar appointments until the WBS is complete. This approach allows all members of the planning team to pay particular attention to the WBS as it is developed, noting discrepancies and commenting on them in real time. Sub-team approach. When time is at a premium, the planning facilitator will prefer the sub-team approach. The first step is to divide the planning team into as many sub-teams as there are activities at level 1 of the WBS. Then follow these steps. The planning team agrees on the approach to build the first level of the WBS. The planning team creates the level 1 activities. The team is split into sub-teams with a subject matter expert leading each sub-team in further decomposition of the WBS. The sub-team continues decomposition until each activity within the level 1 activities meet the WBS completion criteria. Reassemble as a team and report your part of the WBS to the whole team. The entire planning team decides on the approach for the first level breakdown. After that, the group is partitioned into sub-teams, with each sub-team having some expertise for that part of the WBS. It is hoped that they will have all the expertise they need to develop their parts of the WBS. If not, outside help may be brought in as needed. Be careful not to clutter the team with too many people. When the sub-teams have reassembled into a whole team, pay close attention to each presentation and ask these questions. Is there something in the WBS that I did not expect to see? Is there something not there that I expected to see? The focus here is to strive for a complete WBS. Bottom-up approach. Another approach to identify the activities in the project is to take a bottom-up approach. This approach is more like a brainstorming session than an organized approach to build the WBS. The bottom-up approach works as follows. The first steps are the same as those for the top-down approach. Namely, the entire planning team agrees to the first level breakdown. The planning team is then divided into as many sub-teams as there are first level activities. Each sub-team then makes a list of activities that must be completed in order to complete the first level activity. To do this, they proceed as follows. Someone in the sub-team identifies an activity and describes it to their teammates. If they agree that it is a part of the WBS, then the activity is written on a slip of paper and put in the middle of the table. The process repeats itself until no new ideas are forthcoming. The sub-team then sorts the slips into activities that seems to be related to one another. This grouping activity should help the sub-team add missing activities or remove redundant ones. Once the subteam is satisfied it has completed the activity list for the first level breakdown, their work is done. Each subteam then reports to the entire team the results of its work. Final critiques are given, missing activities added, and redundant activities removed. Intermediate WBS for large projects. For every large projects, you may be tempted to modify the top-down approach. While I prefer to avoid modification, difficulty in scheduling people for the planning meeting may necessitate some modification. As project size increases, it becomes unwieldy to build the entire WBS with the entire planning team assembled. When you are in this situation, begin by following the old team approach and decompose the WBS down to level 3. Assign activity managers to each level 3 activities and adjourn the planning session. The level 3 activity managers are charged with completing the WBS for their part of the project. They will convene a session to complete that work. The planning facilitator will then consolidate these level 3 WBSs into the WBS for the entire project. The full team can be reassembled and the planning process can continue from that point. Criteria for completeness in the WBS. In this video, we are going to see about criteria for completeness in the WBS. 6 criteria to test for completeness in the WBS. The following sections look at each of these characteristics in more detail. Start or completion is measurable. Start-end events are clearly defined. Activity has a deliverable. Time and cost are easily estimated. Activity duration is within acceptable limits. Work assignments are independent. Start or completion is measurable. The project manager must be able to ask for the status of an activity at any point in time when the activity is open for work. If the activity has been defined properly, that question is answered easily. The answer should consist of what has been done, how much time was required to complete the work, how much remains, and how long it will take to complete. Start-end events are clearly defined. Each activity should have a clearly defined start and end events. Once the start event has occurred, work can begin on the activity. The deliverable is most likely the end event that signals work is closed on the activity. If those events are not clearly obvious, the activity needs to be further decomposed. Activity has a deliverable. The result of completing the work that makes up the activity is the production of the deliverable. The deliverable is a visible sign that the activity is complete. This could be an approving manager's signature, a physical product or document, the authorization to proceed to the next activity, or some other sign of completion. If the activity does not result in a deliverable, the activity needs to be further decomposed. Time and cost are easily estimated. This is a relative characteristic. A very little experience or knowledge of the activity, in which case easily estimated, will be very different than the case where the activity is one that has been repeated many times and is well understood. In any case, each activity should have an estimated time and cost of completion. Being able to do this at the lowest level of decomposition in the WPS allows to aggregate to higher levels and estimate the total project cost and the completion date. This experience at lower levels of definition gives a stronger base on which to estimate activity cost and duration for similar activities. Activity duration is within acceptable limits. While there is no fixed rule for the duration limitation of an activity, common practice is to set the limit at 2 weeks. Again, this is a relative limit. For very long projects, some limit greater than 2 weeks will be appropriate. There will be exceptions when the activity defines process work, such as will occur in many manufacturing situations. There will be exceptions especially for those activities whose work is repetitive and simple. Work assignments are independent. It is important that each activity be independent of other activities in the following sense. Once work has begun on the activity, if it is independent of other activities, the work can continue without interruption and without the need of additional input or information until the activity is complete. This allows the project manager to schedule the work contiguously, but it can be scheduled otherwise for a variety of reasons. To schedule it in parts because of resource availability, but it could have scheduled it as one continuous stream of work. Estimating activity resources requirements. In this video, we are going to see about estimating activity resources requirements. Any activity needs people or resources in order to be executed and completed. The resource requirements for any activity are estimated by using the Estimate Activity Resources process. The main purpose of this process is to estimate the type of resources needed for a given activity, estimate the quantities of each type of resources needed for the activity. This process too has inputs, uses some tools and techniques, and generates an output. Input to activity resource estimating. The activity list and attributes are the obvious and major input to the activity resource estimating process. Activity list and activity attributes. The activity list, originally developed during the activity definition process, identifies the scheduled activities that need the resources. The activity attributes provide the details for the activities, which will be helpful in estimating the resources. Resource calendars. Resource estimating will require information on the available quantity of resources of different types, such as human, equipment, and material. This information is usually available in the resource calendars, which may also have detailed information about human resources such as skill level, experience, and the geographical location from where the resource will come. Typically, the resource calendar contains the following useful information about the resources: days and times of day when a resource is available, the passive time for the resource, for example, vacation plans for people, the quantity of each type of available resource, the capability of each resource, enterprise environmental factors, information about the infrastructure of the performing organization, such as existing facilities will be used in identifying the resources and their availability, organizational process assets, The organizational process assets useful for activity resource estimating include organizational policies for staffing and purchase of supplies, historical information on what types of resources were used for similar activities in a previous project, and so on. Tools and techniques for activity resource estimating. The tools and techniques that can be used for activity resource estimation are expert judgment, published estimating data, alternative analysis. Alternative analysis is all about exploring alternative solutions to a problem. In the case of estimating resource requirements, it will need to consider alternatives available for resources needed for some scheduled activities. For example, it might need to decide whether it wants to buy or develop a tool needed to perform an activity, what types of machines, for example Windows or Linux, to use, which computers to use to do the development, or what level of skills is needed, etc. Bottom-up estimating. It might discover that it is rather complex to estimate resources for a given scheduled activity. If the problem is inherent to the activity, it might be helpful in certain cases to decompose the activity into smaller components for the purpose of resource estimating, and then estimate the resource for each component, and then aggregate the resources to get an estimate for the whole activity. In aggregation, it must consider the possible relationship, that is, overlaps and other dependencies among different components of the activity, so don't double count the resources or consider a seamless summation of smaller component estimates. Expert judgment. Expert judgment can be used to assess the input and determine the output of the resource estimating process. Published estimating data. Information published by various vendors such as costs for resources can be useful in estimating the resources. Project management software. Depending upon the sophistication of the resource requirements and the capabilities of the available features, project management software might be useful in estimating and managing the resources. It can also create resource breakdown structures. Output of activity resource estimating. The resource requirements are the major output of the resource estimating process. The overall elements that are the output of this process are activity resource requirements, resource breakdown structure, updates to project documents, activity resource requirements. The main purpose of the activity estimating process is to determine the resource requirements for each activity, and therefore this is the major output item from this process. Identify the types of resources required to perform each activity and estimate the required quantity of each identified resource. If a Word package in the WBS has multiple activities, the resource estimates for those activities can be aggregated to estimate the resource requirements for the work package. The requirement documents may also include information such as the basis for each estimate, the assumptions made for the estimate, and the availability of the resources. Resource breakdown structure. The resource breakdown structure, RBS, is a hierarchical structure of resource categories and types required to complete the scheduled activities of a project. The RBS can be used to identify and analyze the project human resource assignments. Updates to project documents. The identified types of required resources for an activity and the estimated quality for each identified resources become activity attributes and must be added to the attribute list for the activity. Activity resource estimating might generate modifications to the activity list. It may also cause to change the resource calendar. Cost estimation techniques. In this video, we are going to see about cost estimation techniques. Estimation techniques. There is no simple way to make an accurate estimate of the effort required to develop a software system. Make initial estimates on the basis of a high-level user requirements definition. The software may have to run on unfamiliar computers or use new development technology. The people involved in the project and their skills will probably not be known. All of these mean that it is impossible to estimate system development costs accurately at an early stage in a project. Furthermore, there is a fundamental difficulty in assessing the accuracy of different approaches to cost estimation techniques. Project cost estimates are often self-fulfilling. The estimate is used to define the project budget and the product is adjusted so that the budget figure is realized. Any controlled experiments with project costing where the estimated costs were not used to bias the experiment. A controlled experiment would not reveal the cost estimate to the project manager. The actual cost would then be compared with the estimated project costs. However, such an experiment is probably impossible because of the high costs involved and the number of variables that cannot be controlled. Nevertheless, organizations need to make software effort and cost estimates. To do so, one or more of the techniques described in figure may be used. Boehm, 1981. All of these techniques rely on experience-based judgments by project managers who use their knowledge of previous projects to arrive at an estimate of the resources required for the project. However, there may be important differences between past and future projects. Many new development methods and techniques have been introduced in the last 10 years. Some examples of the changes that may affect estimates based on experience include distributed object systems rather than mainframe-based systems, use of web services, use of ERP or database-centered systems, use of off-the-shelf software rather than original system development, development for and with reuse rather than new development of all parts of a system, development using scripting languages such as TCL or Perl, that is Osterhart 1998. The use of case tools and program generators rather than unsupported software development. If project managers have not worked with these techniques, their previous experience may not help them to estimate the software project costs. This makes it more difficult for them to produce accurate cost and schedule estimates. You can tackle the approaches to cost estimation using either a top-down or a bottom-up approach. A top-down approach starts at the system level. Start by examining the overall functionality of the product and how that functionality is provided by interacting sub-functions. the costs of system-level activities such as integration, configuration management, and documentation are taken into account. The bottom-up approach, by contrast, starts at the component level. The system is decomposed into components and estimates the effort required to develop each of these components. Add these component costs to compute the effort required for the whole system development. The disadvantage of the top-down approach are the advantages of the bottom-up approach and vice versa. Top-down estimation can underestimate the cost of solving difficult technical problems associated with specific components such as interfaces to non-standard hardware. There is no detailed justification of the estimate that is produced. By contrast, bottom-up estimation produces such a justification and considers each component. However, this approach is more likely to underestimate the costs of system activities such as integration. Bottom-up estimation is also more expensive. There must be an initial system design to identify the components to be costed. Each estimation technique has its own strengths and weaknesses. Each uses different information about the project and the development team, so using a single model, this information is not accurate and final estimate will be wrong. For large projects, should use several cost estimation techniques and compare their results. If these predict radically different costs, probably do not have enough information about the product or the development process. Looking for more information about the product, process, or team and repeat the costing process until the estimates converge. These estimation techniques are applicable where the requirements document for the system has been produced. This should define all users and system requirements. Therefore, make a reasonable estimate of the system functionality that is to be developed. In general, large systems engineering projects will have such requirements document. However, in many cases, the cost of many projects must be estimated using only incomplete user requirements for the system. This means that the estimators have very little information with which to work. The requirements analysis and specification is expensive, and the managers in a company may need an initial cost estimate for the system before they can have a budget approved to develop more detailed requirements or a system prototype. Under these circumstances, pricing to win is a commonly used strategy. The notion of pricing to win may seem unethical and unbusinesslike. However, it does have some advantages. A project cost is agreed on the basis of an outline proposal. Negotiations then takes place between client and customer to establish the detailed project specification. This specification is constrained by the agreed cost. The buyer and the seller must agree on what is acceptable system functionality. The fixed factor in many projects is not the project requirements but the cost. The requirements may be changed so that the cost is not exceeded.